Valence bond theory. Electrons have a specific energy and they occupy certain regions of space within the atom. The basic idea of valence bond theory is that a covalent bond is formed when two atomic orbitals overlap. Each of the overlapping orbitals has one electron in it ordinarily, unless it's a coordinate covalent bond where both electrons come from one atom. And these two electrons are shared between the two atoms in the region where the orbitals overlap. So let's look at an example with H2 molecule. Hydrogen has 1s1 electron configuration. So if those 1s1 electrons overlap, we get a covalent bond between the hydrogens. And the strength of the covalent bond is proportional to the overlap, which is right there. H2S molecule. Hydrogen is 1s1. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. What I've done is I've separated the p subshell into its three orbitals. Remember, we drew three boxes for the p subshell. Those are the orbitals, and they're called 3px, 3py, and 3pz. Well, in order to form a bond, an orbital can only have one electron in it. So I separated 3p4 into the px, py, pz to show you that the 3px has one electron, so I can form a bond there. I can also form a bond here with the 3py orbital because it's got one electron in it. And so what happens is the 3p orbitals that have one electron overlap with the hydrogen, and you form two covalent bonds with hydrogen. Methane, CH4. Hydrogen's 1s1, it's going to overlap with carbon. I've separated the carbon's 2p into 2px and 2py to show you that there are single electrons in those two orbitals. Now, since there are only two orbitals with a single electron, we might expect carbon to only form two bonds. But we know that CH4 is formed. We know that there are four bonds in CH4. And so what we're going to do is we're going to promote an electron from a 2s to a 2pz orbital. So instead of 2s2, it's now 2s1, and now I have a 2pz. And now that you see that there are single electrons in four orbitals, and so I can form four bonds. Now when we overlap hydrogen's 1s orbitals with a 2s and three 2p orbitals, that could give rise to two different kinds of bonds. But all four carbon-hydrogen bonds in methane are identical. So how does valence bond theory explain the structure of this molecule? Well, one of the characteristics of electrons is that they possess wave-like properties. And one of the properties of waves is that two or more waves can interact with each other to form a new wave. The wave functions representing atomic orbitals can be combined to give new functions that are referred to as hybrid orbitals. So in the case of methane, we are forming four equivalent sp3 hybrid orbitals, and they are identical bonds in methane, identical carbon-hydrogen bonds. So the hydrogen 1s orbitals overlap the carbon sp3 hybrid orbitals at the corners of a tetrahedron. And so we have four identical bonds formed in CH4. Now, hybrid orbitals are formed by the central atom. So carbon forms hybrid orbitals, sp3. The hydrogen uses atomic orbitals, the 1s. PCl5 molecule. Phosphorus is going to form 5 bonds with chlorine. What I've done is I've given you the electron configuration for phosphorus, and I've separated the p subshell into px, py, pz, and I've also promoted an s electron up to the d subshell. And so this is going to give me 5 sp3 hybrid orbitals that can be formed with phosphorus. And so when you look at the model for PCl5, phosphorus forms 5 identical sp3d hybrid orbitals with chlorine, and chlorine uses the atomic orbital 3p to bond to the phosphorus. So here's the important part of valence bond theory. Types of hybridization of atomic orbitals. This is what you need to know. The number of hybrid orbitals, it goes from 2 to 6. You need to know the sp, sp2, sp3, sp3d, and sp3d2. Let me give you a couple examples. This chart is really what you need to know. Before this, it was kind of the theory behind valence bond theory. you will draw a structure. Let's say you have SCl2. First thing you're going to do is draw the structure for SCl2. Without drawing all the electrons around chlorine, here's what you have around the central atom, because only central atoms form hybrid orbitals. If I want to know the hybrid orbital around sulfur, I simply count up the pairs of electrons, and lone pairs do count. So sulfur has 4 pairs of electrons, and so the hybridization around sulfur is sp3. It's as simple as going back to this chart right here. You don't really have to know the theory, even though I kind of gave you the theory before this. Let's say you have CO2. CO2 forms, I'm just going to do the dashes here, CO2 forms 2 double bonds. Well, a double bond counts as 1 when you're doing hybrid orbitals. So in this case, carbon only has 2 bonds, and we would say carbon in this case is sp hybridized. So, important thing, know the chart. Lone pairs count, double and triple bonds count as 1 when you're doing hybrid orbitals. And only the central atom forms hybrid orbitals. Okay, let's look at ethene molecule, C2H4. Now this molecule has a double bond in it. And so we could go back to that chart. Each carbon forms 3 bonds. So we would say each carbon is sp2 hybridized. And that's kind of what I've outlined here with the electron configurations. You can see where we get the sp2 hybridization. I've underlined it. But we also have this extra over here we'll get to in just a minute. So we have the sp2 hybridization around each carbon. Notice the overlap here. This is called end-to-end overlap. These bonds here with the hydrogen and the 2 carbons bonded together are called sigma bonds. End-to-end overlap, sigma bonds. Well, you have 1 electron that's left over in that 2pz, and these orbitals are going to overlap sideways above and below the bonding axis to form what's called a pi bond. So there's 2 types of bonds, sigma, which is end-to-end overlap, and pi, which is side-to-side overlap. You only get pi bonds when you have a double or a triple bond. Everything else is a sigma bond. So even in a double bond, you have a sigma bond, but you also have 1 pi bond. And finally, let's look at ethyne molecule. Now this molecule, C2H2, has a triple bond. It looks like this. The hybridization around each carbon is sp, because each carbon has 2 bonds. And I outlined where we get the sp. You notice that you have some extra orbitals here that are left over, py and pz. These are going to overlap side to side and form 2 pi bonds. And so when you have a triple bond, you have a sigma bond, which is the end-to-end overlap, but you also have 2 pi bonds, which overlap side to side. And this is a diagram of that C2H2 molecule.